So welcome everyone to a new episode of the Shannon channel. I'm really happy today to have Hessam Mahdavifar from University of Michigan. And Hessam is going to talk about new phases of channel coding, 5G and beyond.
Thanks, Salim, for the introduction and inviting me to this awesome seminar series. I'm going to just share my screen and start. All right. Okay, is this good?
Yes.
All right, great. So I'm very excited to talk about some new phases of channel coding motivated by 5G and beyond 6G and so on. So first, let me start with an overview of the talk. I will start with a very brief history on channel coding. And then I will talk about the latest agreements for channel coding in 5G. And then I will talk about two emerging scenarios that I have been recently working on. One is the case of non-stationary channels, and the other one is the case of low-capacity channels. And these are both, largely unexplored areas in terms of channel coding. And we think that they are becoming increasingly important with recent advances in 5G. So in particular, for non-stationary channels, I'm going to talk about polar coding for non-stationary channels. And there I will try to provide a brief overview of polar codes. And then I will talk about the scheme that I have to achieve the average capacity for non-stationary channels. And I provide some finite length scaling analysis of the coding schemes. And the third part, I will talk about channel coding at low capacity. And this is joint work with my colleague Hamad Hassani at Penn and our PhD students. So we will talk about fundamental limits of channel coding at low capacity and code constructions. All right. So I guess this is a Shannon talk series, so it's appropriate to start with the picture of our legend Shannon and his breakthrough work that every communication channel can be characterized by a single number C, which we call channel capacity. And it's possible to transmit information reliably over this channel as long as the rate of communication, which is defined as the number of information bits divided by the number of channel users, is less than the capacity C. I'm going to define reliability in a second. And so the way to do this is by using the codes, in particular by doing encoding and decoding. So suppose we have some message U, and these are all vectors, U, X, Y, U hat, they are all vectors. And then we encode the U to X. We transmit X through the communication channel, meaning that each entry of X is transmitted through one independent instance of the channel. We receive Y, and then we have a so-called decoder, and we try to map Y to the message U. So hopefully U hat is equal to U most of the time. And then the reliability condition is that we want the U hat, the probability that U hat is not equal to U to go to 0 as the number of channel users goes to infinity. So motivated by this, let me give some very brief overview of the channel coding and the road to capacity. So it was started by Hamming in 1950, the first class of explicit codes that we know of. And then from there, mainly two branches of coding are started. One is called algebraic codes. The other one we can classify as codes and graphs. And algebraic codes, algebraic structures such as polynomials are used to encode and decode the message. And on the other hand, codes and graphs, we use trellises and graphs to encode and decode messages. So on this side, we have Reed-Muller codes, and then we have Reed-Solomon BCH codes. On the other side, we have convolutional and then turbo codes and LDPC codes. So each of these codes have their own applications. So for example, Reed-Solomon codes are used in storage devices and distributed storage systems. Same as BCH codes, they're used in flash memories. Convolutional codes are used in satellite communication. Turbo codes were used in 3G, 4G cellular systems. LDPC codes were used in Wi-Fi. But despite all these advances, none of these codes were actually provable to achieve the capacity with explicit construction and low complexity encoding and decoding. So finally, polar codes were invented in 2009. And with polar codes, we can achieve the capacity using explicit code constructions and low complexity encoding decoding. So I cannot exactly classify polar codes as being algebraic or being code and graph because they have ingredients from both sides. So from construction perspective, they're closely related to read Muller codes. But from the decoding perspective, they use some more advanced methods of doing decoding on trellises. So they have ingredients from both sides. All right, and if we look at the cellular standard development in the past few decades, we have started seeing codes as soon as we transition from analog to digital. So in 2G, we had the transition from analog to digital, and there convolutional codes were used for reliable communication. And then 3G, 4G, mainly convolutional codes and turbo codes were used. And in 5G, now we are going to use polar codes and LDPC codes. And in each of these generations, we observed a significant improvement in the data rate. So for example, in 4G, we have the data rate around 100 megabits per second, but in 5G, this will be 100-fold, and we will have data rates up to 10 gigabits per second. So the main thing that happened, one of the main things that happened in 5G was the decision to incorporate polar codes and LDPC codes. And that essentially means reforming the entire channel coding paradigm and everything that is around them, such as the designing and modulation together with codes and all that. Okay. And this is not something that happens very often. I mean, so for example, from 3G to 4G, codes basically remain the same, but now from 4G to 5G, we have such a major reform. And so one question here from this picture is, okay, if 5G already looks like some advanced human being, what would 6G look like? So to me, probably it would be some alien, which we don't know what that would be. But hopefully by 2030, we'll figure that out. All right. So, so here is a summary of some of the agreements for coding in 5G. So the first official agreement was made in late 2016. And basically, it was decided that LDPC codes will be used for data channels in the so-called EMBB, which is the main scenario for mobile communication, and for both uplink and downlink. And also polar codes are being used for control channel uplink. Later on, they were also decided to be used for downlink. And besides that, I was also looking at the most recent agreements. So these are all summarized in this new radio document on the multiplexing and channel coding. This is from the latest, one of the latest versions in September 2019. So the agreements are that polar codes are going to be used for the so-called physical uplink shared channel and also physical broadcast channel. Okay. So when we talk about these channels, doesn't mean that they have they are like physically different and with different characteristics. It just means that they use we have this so-called OFDM grid that we are going to we are always using for cellular communication. So some of these OFDM symbols are being assigned for example, for data channels. Some of them are being assigned for control channel. As long as users are synchronized to the network, they know where to look for, where to look at to get the information, for example, for the control channel and so on. Okay, so these are basically just means that they are physically separated. But they're all using OFDM on the same frequency and band. Okay, so when we talk about control channel, let's see what that really is. So the control channel contains information that are essential to initiate the communication. So for example, the user will know where their information is in terms of where to look for, which resource allocation, which OFDM resource allocations to look at. And also, what are the modulation orders? For example, is it QPSK, 16 com, 64 com, so on? What is the coding rate? What is the HRQ information? And so what we really need is that we want it to be very reliable. So that's what we care about the most. So that's why we don't really go into higher modulation. So we just stick to QPSK modulation. And when they were deciding about which codes are the best to pick for the control channel in 5G, so basically they consider some certain scenarios. And so they looked at the code rates of these range, so as low as 1/24 and as low as high as 2/3, and also the information block length up to 200. So it's rather small, but it's much longer actually than LTE. So I think LTE, the maximum code block length was around 40 or something. So for 5G, we will need more control information bits. Okay. And all these codes, like Turbo, LDPC, Polar, they were all being compared together. So for example, I'm just including one figure from one of the contributions by wireless companies, and there were like hundreds of such simulations. So for example, here we are looking at the number of information bits 64, and we are looking at Polar and LDPC. LDPC, we have two types, type 1, type 2, and they just have different structures. And for example, if you want to look at one case, so for example, on the left-hand side of this plot, we have rate, I guess, rate 1/12. And so we can see that polar codes, so the red ones are polar codes with different list sizes. And then the purple one is the LDPC code. So there's like a 2 dB gap, which is considered very huge in channel coding. So yeah, so basically polar codes were really the best in these regimes. Very short block lengths, and when we want the very reliable communication. So that's why actually they were decided to be the main coding scheme for control channel.
Hey, Sam, I have a question. So
Sure.
how bad, for example, is, since here the number of bits is very small, how bad is just simple replication or?
So yeah, I guess repetition is there, but for very small lengths, maybe if you have only a couple of bits to transmit. So that's what actually one of the decisions. It's very small though, but here it says that for future studies, very small block lengths, very repetition block coding may be preferred. Okay. So yeah, but this is back from 2016. I don't have the most recent information on this, but I assume because I had seen this in 4G that we use repetition for very small block lengths, maybe up to 10, I don't know. But for larger ones, maybe when you have like few tens or 100 bits, then really, these coding schemes can be much better. Yeah. But thanks for
in terms of because what do you care about? Like, is it the power? Like, you care about the rate because you're trying to minimize?
We don't care about the rate that much, but we still care about the rate because we care about latency. Okay.
Okay. So
yeah, latency, because if you cannot decode the control channel, right away, and it takes time, you may miss a few frames of your data. Okay. So latency is very important. All right. So, and 5G, it's not really just about the so-called eMBB, which is the main scenario for mobile communication, but there are other scenarios. One is ULLC, ultra reliable low latency communication, and the other one is MMTC, massive machine type communication. And each of them have different limitations and different requirements. So there are really many more scenarios than we used to think about in 5G. So, and motivated by some of these new scenarios, I'm going to look at two new problems from channel coding perspective. So one is the non-stationary scenario, and here is the setup. So the setup is that we have n channels, okay, and we are going to transmit n bits. Okay, so the number of bits we are going to transmit is exactly equal to the number of channels. So each bit goes through one of these channels, and we assume that these channels are known at both the transmitter and the receiver a priori. Okay, so what is the motivation? From the 5G perspective, so 5G, we have several new features to enhance the spectrum efficiency, for example, carrier aggregation. So basically, you can aggregate up to 16 carriers at different frequency bands for your communication. And each of those bands will have different characteristics. The other one is massive MIMO. So for example, we'll have up to 64 by 64 massive MIMO. And also we'll have higher order modulation, maybe up to 1024. So for example, if you imagine a very optimistic scenario that we will have maybe 64 by 64 MIMO, we will have maximum number of carriers, 16 carriers, and 256 com modulation, then we basically have 64. So suppose that we just decompose our MIMO into 64 parallel channels, 64 times 16, number of carriers, times 4, which is the number of parallel channels from the 256 com modulation. So 256 com modulation, we will get actually 4 pairs of different channels. So we get 8 channels, but 4 of them are different. So we get like up to maybe 4,000 almost independent channels. So that's a lot of, that's a lot of channels, and each of them have different characteristics. So we are really going towards such scenarios where we need to transmit across different channels at the same time. Okay. So that's one scenario. The other scenario is the what we call low capacity channels. Okay. So I have 2 motivations to look at low capacity channel. One is the so-called narrowband communication, which is the main scenario for the so-called narrowband IoT or NB-IoT. This is a feature that the standard has introduced in order to connect IoT devices into the cellular network. And so it is expected that we are going to have 1.5 billion NB-IoT devices, and we are going to serve many devices in one cell. So we want to have the potential to serve up to 50,000 IoT devices in one cell. And we also want to tolerate up to 170 dB coupling loss. That's almost like 20-25 dB more than regular LTE scenarios, because we want to have maybe IoT devices in very remote areas, and these are very low power. And so if we translate this into SNR of the channel, after considering antenna gains and so on, we'll be dealing with SNRs, effective SNRs as low as minus 13 dB. And if we translate it into the capacity, which is which is more familiar for us, it's like 0.03. So that's a very small capacity. So the other scenario is actually the other extreme, which is the wideband communication. So for example, millimeter wave. Okay, and millimeter wave is one of the main enabling technologies of 5G, in which we are going to higher frequencies, and we'll have a much larger bandwidth. So for example, we'll have maybe 1 gigahertz bandwidth for one user. Okay, so and millimeter wave channels are very different than classical AWGN channels, but let's for simplicity just look at some AWGN channel model. And when we look at it in the case of being wideband, so when the bandwidth B is very large and goes to infinity, suppose that we have like a constant power and the B goes to infinity, then essentially what it means is that the SNR is going to 0. Okay. So what it means is that in wideband scenario, assuming a constant power, we will have a high data rate in terms of bits per second, but the individual bits that we are going to transmit, they will be going through channels with very small SNRs. Okay, so basically what it means is that now, if we look at these 2 extremes of communication, one is the narrowband, the other one is wideband. Interestingly, in both scenarios, we're going to dealing with low capacity channels, low SNRs and low capacity channels. Okay. So these are the motivations for the specific problems that I'm going to look at in this talk. So in this part of the talk, I'm going to look at polar coding for non-stationary channels. Okay. All right, so let me provide a very brief overview of polar codes. It probably requires one entire talk, but I will try to be brief. Suppose that we want to transmit 2 bits across 2 independent copies of a channel. So this is, for example, the uncoded scenario. And let me, for example, do something on top of this. And instead of just transmitting uncoded, I'm going to transmit U1, U2. But then in the first channel, I transmit U1 plus U2. In the second channel, transmit U2. And if we do that, then intuitively, the channel that bit U1 observes is going to be weaker than the channel that bit U2 observes. And I'm going to define what I mean by channels that these bits observe. Okay. So if we do this one more time and do this recursively, now we have 4 bits, each of them. So U1, U3 go through this one of these operations, also U2, U4, and then U1, U2, and then U3, U4. Okay. So we will have 2 levels of such operation. And if we do that, then the channel that U1 observes is going to become even weaker, and for U4 is going to be even stronger. So we can keep doing this, again, recursively, and we can kind of expect that some of the bits are going to observe stronger and stronger channels, and some of the bits are going to observe weaker and weaker channels. And if we look at this transformation from UIs to XIs, although we have such recursive structure, what it really is just some linear transformation, right? Which we can represent using a matrix. And if we want to do that, we can look at some base matrix G, which is just 1, 0, 1, 1. And then we just look at the Kronecker powers of this G, which are defined recursively. And so, for example, the transformation from UIs to XIs is just by multiplying the vector of UIs by G to the Kronecker power 3. So, so I was talking about the channels that bits observe. So here's a more precise definition. So for example, if we look at bit UI, and the channel that the bit UI observes, we define it as follows. So on the output of this channel, we have all these YIs, which are the outputs of the channel, the independent copies of the channel. Also, we have all the bits U1 up to UI minus 1. So we assume that some genie gives them to the decoder. Okay. So the reason that it makes sense to define the channel like this is that for polar codes, we are going to use the so-called successive cancellation decoding, in which we decode bits 1 by 1. So when we are decoding bit UI, we assume that all the previous bits U1 up to UI minus 1 are already decoded, hopefully successfully, and they are already available at the decoder. Okay. And then here is the perhaps the main channel polarization theorem by Arkan, which says that surprisingly, if we just increase n, the number of the block lengths, then the channels start polarizing, meaning that they become either noiseless with capacity 1 or pure noise with capacity 0. And also the fraction of noiseless channels is approaching the capacity. So if you want to see how this actually works, I have some numerical example. So this is a binary erasure channel with capacity half. So on the y-axis, I'm showing the capacity, and on the x-axis, I have the bit channels, but sorted. Okay, sorted with respect to the capacity. So it doesn't really, the capacity is not really increasing with the indices. So I'm just sorted them so that we can see how it's changing. So here we have only 16. The block length is 16, the capital N. And then here we have 64. And then here we have 2 to the 8, 2 to the 10, and 2 to the 12. Okay, so we can see that as we are increasing the block length, more and more channels are going to be either around capacity 0 or capacity 1. And if n goes to infinity, then this actually becomes a sharp transition from 0 to 1. And so the ones that are closer to capacity 1, we call them good bit channels, denoted by Gn of W. And the ones that are closer to 0, we call them bad bit channels, denoted by Bn of W. And here is the idea to construct the code, because once we have the channel polarization, now we have to describe what the actual code is. So the idea is that we are going to transmit the information bits over the good bit channels, the one that have no capacity 1 and hopefully can be decoded successfully. The ones that are bad, we are just going to freeze them to zeros. So we don't send any information over those channels. Okay. So let's see an example of polar codes. As I said, the polar codes are constructed from these from this base matrix G and its Kronecker powers. So what it really is, if you're just familiar with the linear concept of linear codes, the generator matrix of polar code is really just a submatrix of this, this large matrix. So when we want to construct a code, let's say of dimension k, when we are transmitting k information bits, all we are doing is just selecting k rows of this G. Okay. So for example, if we are looking at the case,
Hi, Mahdi. We cannot hear you, Hessam.
oh, okay.
Yeah, you may have muted yourself by mistake, maybe. Now we can hear you.
Okay, yeah, because I'm using this microphone and it seems that it's low in battery. So,
okay.
Yeah, sorry. So maybe I can switch to my my computer microphone.
Yeah, because I was just looking at my keyboard trying to figure out what wrong button I pressed, and then Ali sent the message.
Okay. Do you hear me now?
Yeah, we hear it perfect. Yes.
Yeah. So, sorry. Yeah. It looks like it's eating battery a lot because I just changed the battery. So, yeah. But I'm going to just use my computer's microphone. Hope that the quality is good.
Yeah, it's not bad actually. Yeah.
Yeah. Okay. So yeah. So we are going to construct a polar code of dimension 4 here, and so what it means is that we are going to select 4 rows of this 8 by 8 matrix according to some criteria, and so the criteria can be different. For example, the capacity of the bit channels that we define, or the error probability of the bit channels that we define. So anyways, it looks like for this example, we need to freeze the inputs to first, second, third, and fifth channel to zeros, and the rest we are going to transmit information. So we can just assume that, okay, we still have this vector of length 8, and 4 of them are zeros, and 4 of them are information bits. So we can still use the same block diagram to do the encoding, which is pretty fast because it kind of resembles the FFT structure and can be done with very low complexity algorithms. Okay.
So how did you know which rows you're gonna freeze?
So yeah, I guess for this one, it really depends on the channel, right? So I didn't really specify the channel here, but actually most of the time for this code, for this rate, these are the best ones. I cannot say that it's always the best one, but yes. So for example, if we look at the binary erasure channel, erasure probability half, these are the best ones. Yeah. So we can set the different criteria. For example, we can look at the capacity of the bit channels that we define, or if we are really caring about just the block error probability, it's better to stick to the so-called probability of error of these bit channels, and we just try to pick the ones that have the lowest probability of error. of course, we need to do that given the channel. Yeah. So that's what is what is different with polar codes. The polar code construction is channel specific.
And you by saying channel specific, you mean you need for a binary erasure channel, you need the erasure probability.
Yes, we need the erasure probability. Not only we need the class of channel, but we also need the specific parameter of the channel. So, for example, just knowing that it's BECIE or BSC is not sufficient. We also need to know the exact parameter of the channel.
And are these very sensitive to? Let's suppose I take if the erasure probability is 0.51, would you expect these things to change dramatically?
Well, no, not. Well, yeah, there are a lot of research on this. It can be sensitive if you change the channel class, let's say from BC to BSC, but within the same class, it is kind of robust. So that's why when we are constructing the code, so for example, if we are constructing the code for BAWGN, then we construct the code for a certain SNR. So I optimize my code for that SNR. And then, because it's not really feasible to change the code when the SNR changes. So we fix the code, but when we simulate it across different SNRs, we get pretty robust performance curve. And so, yes, so it's kind of robust with respect to the parameter of the channel. But when we look at different classes of channels, it can be very different. Yeah. Okay, thanks for the question. All right. So one question that I'm looking at it here is that can polar codes achieve the capacity limit in more general models than the original one considered by Archon? So the original one considered by Archon was the class of binary input, discrete, memoryless channels. Okay, and since then, these results, the channel polarization and capacity achieving results, have been extended to non-binary, asymmetric, and also channels with memory. So what I'm now looking at is, can this be extended to the non-stationary case, where the channel is different for each transmitted bit? Okay, and like I said, I have some practical motivation to study this problem from 5G perspective. But also, there is some theoretical motivation. Since Archon's work, we have always been interested in seeing, okay, how much we can generalize this to more extended classes of the channels. All right. So again, just to recall the non-stationary model, it's the model where we have n channels, W1 up to Wn, and we want to send n bits across these channels. And hopefully, what we want to get is a rate that is close to the average capacity. Okay, so we want a rate that is close to the average capacity. Shannon tells us that this is the limit of the information and amount of information that we can transmit across these channels. But can we actually get close to this? Okay. So my main theorem says that yes, it's possible to do that with polar codes. And although I need to change the construction of the polar codes in order to arrive at this result. And in this theorem, not only I show that I can get to this average capacity, but also I can show how fast I can get to this average capacity. Okay? So in other words, if I fix some probability of error, PE, for my block error probability, and then I look at the rate of my code, I can guarantee that my rate is away from the capacity by something that is proportional to n block length to this some power, so some polynomial of n. And this parameter mu, we tend to think about it as this so-called scaling exponent. I'm going to talk about it from the finite length analysis perspective. And we like this mu to be as small as possible. For random codes, it's going to be 2. I'm going to talk about it. But we want it to be as close as to this 2. But for this theorem, I can bound it by 8.54, which is still finite. So as long as it's finite, actually, I'm very happy. Okay. So so this in order to talk about this result in more details, I need to talk about this finite length analysis framework. So in general, in such framework, we are dealing with this question that given a channel W with capacity C, what is the minimum possible block length N that we need in order to achieve a rate R and the fixed probability of error P. Okay, so if we fix the probability of error and the rate, what is the block length N that we will need to transmit? Okay, so the answer is given by the series of work back in 60s, and also the work by Polyansky, Poor, and Verdu, that if we look at this N, the answer is given by this equation. And in this equation, we are observing some V, which is the so-called some characteristic of the channel. It's a fixed given the channel. It's called channel dispersion. And the Q is just the Q function of the Gaussian distribution. And P is the probability of block error. R is the rate, and C is capacity. So this is one form. The other form we can think about is that the rate is just C minus this, which is order of 1 over square root of N. And you can see when I was talking about the scaling exponent, so this 2 here is the scaling exponent, and we can actually get this by random coding. And for like practical code, we like to see what is the scaling exponent that we can get. Okay, which means that how fast we can approach the channel capacity. All right, and there are a series of works on a scaling exponent of polar codes. So the first by Hessam and others, they established the scaling exponent for BECs, and then for general channels they had bounds, and then the upper bound specifically was improved, and then the lower bound was also improved. The bound for BECie was also improved by going to larger kernels than 2x2 kernels. And then finally, the current result is that if we let the size of the kernel to grow arbitrarily large, then we can actually get to this optimal scaling exponent of 2. Okay, so these are all for the stationary polar codes. Okay, so in order to study this scaling exponent of polar codes, we need to somehow come up with some measure of polarization. So, for example, we need to define some function f of the channel parameter zi. So the parameter of this channel wi, I'm just going to work with the so-called Bhattacharya parameter. It's a parameter that is closely related to the probability of error. It's something between 0 and 1. And then if it's close to 0, it means that the channel is very good. If it's close to 1, it means that the channel is very bad. So then we want the channels to be polarized. We want these z's to be either close to 0 or close to 1. Okay. And with that in mind, I'd like to define some function f in order to capture how polarized these channels are. So for example, I want when the channel is completely polarized, meaning it's either 0 or 1, I want the f to be 0. And I want the f to be maximized when z is half. That is probably the least polarized channel. And if we look at Arikan's proof of polarization, but he doesn't talk about any of these, but implicitly he looks at the evolution of z times 1 minus z. So implicitly in this sort of framework, we can assume that he talks about f being z times 1 minus z. Okay. So I want to look at this, the average of f across all the channels, and then I want to look at it when I do this polarization. So for example, this first level, the top level, are the channels, initial channels, just the channels that are given to us in the non-stationary sequence. And then in the next level, I just combine maybe the first and the second channel, and then the third and the fourth channel, and so on. So the minus operation is the worst channel, and the plus operation is the better channel. And the same way I continue recursively, and I look at this measure of polarization for each polarization level. So I want this measure of polarization to go to 0. Okay. Not only I want it to go to 0, I want it to go to 0 exponentially fast. Okay. So that's why I'm defining these etas. So I define eta jn to be the minus log of the, how much the EJ, the measure of polarization at level j, is reduced compared to the measure of polarization at level j minus 1. And then I talk about, I look at the average speed of polarization when we do this n times. So when we go to the last level of polarization for the given n channels, I'm going to look at the average speed of polarization. And I want it to be lower bounded away from 0. Okay, and if it's such, then I will just call this polarization fast. Okay. So the goal here is to find the lower bound and the speed of polarization. And in order to do this, we need to upper bound expressions of these 4. So Z1, Z2 are the Beyor parameters of W1, W2. And Z12 plus is the Beyor parameter of the better combined channel, and Z12 minus is the Beyor parameter of the worst combined channel. So I want this to be upper bounded away from 1. Okay. All right. So in order to do this, I'm going to just look at a function g that is defined as follows. Okay. And the reason that I define the g as follows is because luckily for the better channel, plus channel, we know that the Beyor parameter is just the product of the Z1, Z2 of the 2 channels. But for the worst channel, the minus channel, we really don't know. It depends on the real-world characteristics of the channel. But what we can say is that Z minus belongs to this interval defined by Z1 and Z2. Okay, so, and because I'm going to look at a worst case analysis, I'm just going to look at the supremum of this function, assuming that Z1 can be anything in this interval. Okay. And so intuitively, if I combine channels that are very different, meaning that, for example, Z1 is close to 0 and Z2 is close to 1, I don't get a good polarization. Okay, meaning that this G function would be close to 1 or maybe even above 1, which we really don't want. Okay, so in order to get a fast polarization, I have 2 ideas that I'm going to do on top of the polar codes. One is that I'm going to sort the bit channels with respect to their Beyor parameter before combining them. And when we are doing this polarization, at each level of polarization, in each sub-block, I'm going to apply this sort. Also, whenever I cannot guarantee that this G is less than 1 or it's greater than 1, then I just skip that combining operation. Okay, which seems, which doesn't seem very intuitive. It seems that, okay, it's going to hurt the polarization. Actually, may be true, but I just need to do this in order to be able to guarantee this fast polarization. Okay, so this skipping operation may actually slow down the polarization compared to the stationary case. So in order to minimize the effect of skipping operation, I'm going to quantize the 0-1 interval into a certain number of subintervals, and I'm going to look at the effect of combining different channels. I'm going to take that into account only when the 2 channels belong to the same interval. And that will help us to minimize the effect of escaping operations when we sort the channels. Okay. So in particular, I can, I'm looking at the splitting of the 0-1 interval into certain subintervals according to some arithmetic sequence and some geometric sequence. And motivated by this, I'm going to define some function h, which is the supremum of this g function when the both parameters belong to one of these subintervals. Okay, so and really at the end of the day, I will just take a look at the supremum of this function h, and that I call eta, and that kind of represents some bound on the speed of polarization that I was looking at. And if we go back to that function f that we had defined for the measure of polarization, for some reason z times 1 minus z doesn't work, and but we can just if we just pick another power like b, which is between 0 and 1, it somehow works. I don't have like an intuition for this. It's just some technical detail of this finite length technique. Okay. So anyways, I'm going to define that eta to be supremum of this minus log of supremum of this h, and this eta by eta plus 1 is going to become a lower bound on the speed of polarization. Okay, so this is the theorem that I have, and so it kind of tells me that I can upper bound this average speed of I can lower bound the average speed of polarization by something that can be arbitrarily close to eta divided by eta plus 1. And this eta is something that we can just play with all these functions that we have in order to get the best eta. Okay. So I'm going to show also some numerical examples. So in particular, I'm looking at BECs. And for BECs, the good thing is that we know both parameters of the plus and the minus channel. Okay. And in this numerical example, I'm looking at 2 to the 20 number of channels. It's very large, so it's not something practical, but I just wanted to show the effect of this speed of polarization. And the non-stationary sequence that I'm looking at is just the arithmetic sequence between 0.01 and 0.99. So it basically covers the entire range of channels. So in this plot, I'm showing the speed of polarization at each level with respect to the polarization level. So polarization level goes from 0 up to 20 because the block length is 2 to the 20. And with sorting, what we can see is that initially it kind of follows, thanks to the sorting, follows the speed of polarization of the stationary case. But at some point it just drops to 0, perhaps because we will start combining very different channels. But if we just look at some random permutation, well, it starts something lower than the stationary case, but eventually it reaches the stationary case because we are just assuming some random sequence. So eventually these sub-blocks that we are dealing with are going to become more and more kind of similar because we are just combining random channels. Okay, but I still don't know which permutation is the best, and actually that's a subject of one of the ongoing works that we are doing. Okay. Okay, and then once we have this fast polarization, actually, in order to construct capacity achieving, we need to do one more step. So we need to look at the so-called two-stage polarization, and so rather technical details. So I'm going to skip maybe these details because I want to get to the last part. And okay, so here is my theorem that kind of relates the scaling exponent, this mu that we have here, to this eta, which was the average speed of polarization that we were talking about. And also in terms of encoding and decoding, one may wonder, okay, with all these changes that we are doing on top of polar codes with permutations and skipping operations, does anything change in terms of complexity? The answer is no. So all we need to do is that when we are doing decoding of polar codes, we tend to show it using this so-called this binary tree. The only difference is that we are going to have some permutations when we are passing back and forth information over this tree. That's all. And also, whenever we are skipping a polarization operation, then we just skip that the corresponding operation on the bit reliability LLRs. Okay. So in terms of complexity, we are good. Also, in terms of the simulation results for BAWGN, I've also looked at a non-stationary sequence of SNRs that are picked, picked here between -2 and 1, and so here I'm just comparing non-stationary with a stationary setup. A stationary setup, the SNR is just fixed, but for the other one, the SNRs are within a range, but the average SNR, so what I'm looking at is just the average SNR. So it's a fair comparison. And what I observed was that, okay, with this sorting and all, the non-stationary case actually works as well as a stationary. So that's a good news that we are just able to do just as well. in the non-stationary scenario. Okay, so there are several open problems. One is that can we actually tighten this upper bound on the scaling exponent? I think it's possible because what I did was to a skip operation, which is which can be probably skipped using some other method, and also one may wonder, can we actually look at the speed of polarization for a certain family of channels, let's say binary Auger channel, exactly characterize that, like what we have already in the stationary case, and also studying the error exponent of polar code. So that's a different story. We always look at the error exponent and the finite length analysis, a scaling exponent, but somehow they can also be combined together. So these are the things that can be looked at. Okay. So hopefully I still have some time to talk about the last part, which is channel coding at low capacity. Okay, so if there are any questions?
No, I think we have maybe roughly 5 more minutes.
Okay, okay, yeah, okay, good. So I try to be quick and just maybe just show the result. Because this is another thing that I have been very excited about, and we have been working on this. This is a setup that hasn't really been looked at much, the low capacity setup, and we have motivations. Like I said, the IoT motivation also wideband. So it's a rather unconventional setup because we tend to think about capacity as something constant, but here we actually look at the capacity as something that can be little of 1. And by little o, I mean with respect to the block lengths, okay? And because we are going to look at everything in finite length analysis, so this actually makes sense. It doesn't make sense to talk about low capacity given this definition asymptotically, but it makes sense to talk about it for finite lengths, okay? So for example, if we look at that wideband communication scenario, the capacity per bit is just given by this, and then assuming some certain modulation, the block length is actually big O of bandwidth, which means that capacity is just big O of 1 over n. Okay, so this is one example of this low capacity scenario. And alternatively, we can look at the actual amount of information that passes through the end use of channel and call that kappa. Turns out to be an important parameter here and more convenient to work with compared to capacity itself. Okay, so we work with this parameter kappa. And in the so-called moderate capacity regime, this is what we already discussed, although it was in terms of rate. Now I'm looking at it in terms of the size of the code. Okay, so this M of N and PE is the largest, the size of largest code that we can have with probability error PE and length N. And so if we just normalize this by N, it would be something in terms of rate here. And again, this is what we call moderate capacity regime. It holds in that regime. So let's see what is going to be different in the low capacity regime. So I guess that's going to be the main message here. And so when we look at the low capacity regime, like I said, this N times C might be just big O of 1. So it's already comparable with the terms that are that we are ignoring. Okay, so this whole formulation actually fails to capture the finite length performance in the low capacity regime. So we need new techniques to analyze finite length analysis here. And also the code designs that we have in the standard, they are based on repetition, which can be inefficient. Okay, so the main result is that we derive non-asymptotic loss for BECIE and BSCs in a low capacity regime. And also we characterize actually the efficient number of repetitions. So it turns out that we can actually repeat, but up to a certain point. And we have the exact answer to that question, how many repetitions we can do. So let's look at the BECIE case. I just give the perhaps the idea of how to do this and then just show these some plots. So for BECIE case in the moderate capacity regime, if you look at the output, For example, in the output, we see a bunch of zeros and ones and a bunch of maybe erasures, and they both happen maybe often. So that's why central limit laws are used to predict the non-asymptotic behavior here. In the low capacity regime, however, most of the time, we actually see erasure. So the information is rarely transmitted through the channel. So we are dealing with the so-called rare information, and that means that in order to get good bounds on the non-asymptotic behavior, we better use Poisson approximation rather than Gaussian approximation. Okay. So with that, which I think is the main message here, I'm going to just skip maybe these details and just show the plot. So in the finite length regime, we have some bounds, the so-called random coding upper bound and the converse bound, but these bounds are not, we cannot exactly compute them because the bounds involve very large numbers that we need to compute. They are not efficient to compute, so we just have to approximate them. And in the finite length regime, we try to come up with a closed form formulas that can be computed accurately. So that's the whole point of finite length. And we have upper bound and lower bound, which can be computed accurately. And we can see that these are the blue curves that follow closely the green curves, the true, the best bound that we know. However, if you just plot the bound promised by Polyansky and others, as we expected, it's not precise. So it gives like a very bad approximation here. And then again, in this plot, we are looking at the block length n versus the erasure probability of the channel, and assuming that we want to just send maybe 40 information bits, and we want to see what is the smallest block length that we can transmit here. Okay. So we get pretty good bounds, and here also I plot polar codes with 12-body list decoding out of curiosity to see how good they are. They are actually very good, so close to the upper bound. And we have similar results also for BECIE, so maybe I just skip them. And also we have very good approximation of the true bounds that we have.
No, I have a quick question. So here, because you mentioned in the last bullet polar code, so are these fundamental bounds, or these are what you can achieve with
these for the polar code? Because
you mentioned polar code at the bottom of the slide, so.
Yes. So the polar codes, they're just numerical. They're just numerical result. Okay. So for example, let's say we simulate a polar code of length 8,000, and with 40 information bits, we get probability of error 10 to the -2. So we just put a point there. Yeah. Okay. So yes, and for BECIE also we have a similar result as well as AWGN. So I don't include AWGN here. And let me maybe just briefly mention the result for the practical code design. So the standard actually what it does, because it wants to use what is already available, the rate 1/3 turbo code for LTE, they just use the same code, but just do a lot of repetitions on top of it. Okay. So of course that can be very inefficient, but what turns out that we can actually repeat up to a certain point without losing much of capacity. Okay. So our result is that if we want to have a loss of capacity at most order of 1/n, then the number of repetitions is like n over k squared or kappa squared. Kappa is n times c, or you can just replace it with k, the number of information bits. Okay, so roughly it means that if you want to send k information bits, if k squared is greater than n, then you better not do any repetition. But if it's less than n, you can just use a code of length k squared, and then the rest of it you just repeat. Okay. And interestingly, if you just construct polar codes naturally, they will apply implicitly this repetition length. That was also very surprising to us. So there are related work on this. So Posner back in 60s, he had suggested that if SNR is very low, actually repetitions are good enough. And then there's also a result by Doomer concatenating polar codes with repetition. Yes, so I guess I'm running out of time here. So the main message was that, okay, we can just repeat up to a certain number of points, n divided by k squared, and polar codes does this actually apply apply this number of repetition, and that is mentioned in our theorem here. And so we can talk about certain open problems in the low capacity regime. Non-asymptotic analysis for general channels in low capacity. Of course, we just have it for certain classes of channels, EC, BECIE, BAWGN. Practical implications in wireless, military wave, people are not talking about terahertz going above 100 gigahertz. I know it may sound crazy, but perhaps for 6G, we will have to do that. And also, when we look at the actual code constructions, can we do better than repetition, maybe by better mechanism or low complexity concatenation mechanism? And if you want to look at low-rate algebraic codes, that means that we are going to look at the normalized minimum distance of half. Okay, so we have, like, for example, with Muller codes, but there are gaps between that we can potentially look at how to fill those gaps and construct low-rate algebraic codes. Okay. And yeah, by that, I will just conclude the talk. Thanks.
Thanks a lot, Hessam. That was very interesting. I'm sorry I rushed you through the end.
No, I mean, that's okay. Yeah.
I think we have a little bit of time for one question. I don't know if anyone has a question.
Hi, so maybe I can ask a question.
Yeah, sure.
So I'm Mustafa from Munich. So if you want to use polar codes for low rate regime, let's say low capacity regime,
sure.
So isn't decoding complexity a bit problematic, because you have like O n log n, right? And
yes.
You have size L times n log n. So if you're using low rate, then does it make sense to use, I don't know, or I mean, did you understand my question?
Yes, I understand, yes. So actually, this becomes interesting, actually, looking at the complexity in the low rate regime, because we tend to think about complexity as something order of n or n log n, where n is the block length. But in the low capacity regime, because the number of information bits k is much smaller than n, I think it makes sense to actually look at the complexity in terms of the k. So k is not necessarily linear with n here, okay? And so that's where actually things become problematic, as you suggested, because now if we look at polar code, although polar code has some repetition, but the block length, we can reduce the block length to k squared, essentially, okay? So because it has some repetition, for those repetitions, you can just sum up the LLRs, okay? And you can just then decode for the code of length k squared. And now in terms of k, the complexity is like k squared log k. So it's rather high. I agree with that. So now, for this kind of regime, we probably need to reduce the complexity. So for example, still I think because the decoding tree is very sparse, we can skip a lot of operations. So that can potentially help in the complexity. But looking at the exact complexity of low rate polar codes, I think it's definitely a very interesting problem. Yeah.
Okay, thank you.
Sure.
Thanks a lot, Hessam, again, and we'll see you everyone next time in the next talk. Thank you.